Happy new week, everybody, and once again, let's try doing this. So you can see the do now is actually the exploration on page 484. I'm just going to run through it for you real quick because the strategy we use on this do now is what we're going to use in this lesson today. By the way, today's lesson, one of my favorite from the entire year. So looking here, I know p of 0 equals 1, p prime of 0 equals 2, p double prime of 0 equals 3, p triple prime of 0 equals 4, fourth derivative at 0 is equal to 5. I also know that p of x is equal to a naught plus a1x plus a2x squared plus a3x cubed plus a4x to the fourth. I will point out to you guys that the subscript on the a corresponds with the exponent of the x. So you can see subscript 0, exponent of 0, subscript 1, exponent of 1, subscript 2, exponent of 2, etc., etc., etc. Again, might seem really easy to point out, but that's going to be important later today. Now, what I do want to point out to you guys is if we do p of 0, that's going to be the same thing as a naught plus a1 times 0 plus a2 times 0 squared plus a3, I don't know why I put parentheses on there, times 0 cubed plus a4 times 0 to the fourth. And what's nice there is notice how everything other than a naught has a coefficient of 0. So those are actually inconsequential here. I actually have p of 0, 1, is equal to a naught. That's pretty cool. Now to find p prime of 0, I first find p prime of x. Well, a naught, that's constant, differentiates out. a1x, well, the x differentiates to 1. I just have a1 plus 2a2x, derivative of x squared, 2x, plus derivative of x cubed, 3x squared, so 3a3x squared plus 4a4x cubed, which, if I find p prime of 0, that's excuse me, didn't mean to cough right at the camera. P prime of 0 is going to be equal to a1 plus 2a2 times 0 plus 3a3 times 0 squared plus 4a4 times 0 cubed. Well, all those have 0 coefficients. That means p prime of 0, 2, is equal to a1. And you can see I tried to space this out, but I don't think I spaced it out appropriately. Oh well, we'll deal. Now to find the second derivative, I can find out that p double prime of x, find the derivative of the derivative, so a1 differentiates out, derivative of 2a2x, well that x differentiates down to 1, this is going to become, let's just call that 2 times 1, a2. I know some of you are going to be annoyed at me for putting that times 1, but whatever. Plus 3 times 2, a3x, plus 4 times 3, a4x squared. So each term has a reduction in power by 1, and that exponent drops down still. So now I can see p double prime of 0 is equal to, 2 times 1. I think I've shown you guys this before, but 2 times 1 actually means 2 factorial a2 plus 3 times 2 a3 times 0 plus 4 times 3 a4 times 0 squared. So we should see, again, trend sticking here. Those cancel out. We end up with, this was double prime, so 3 is equal to 2 factorial a2. So therefore, divide by 2 factorial, I've got 3 over 2 factorial is equal to a2. I keep doing this. I got p triple prime of x, not of 0, is equal to p triple prime would be the derivative of this one, so that's 0. This becomes 3 times 2 times 1, a3, no x differentiates out, plus 4 times 3 times 2, a4x, p triple prime of 0 is equal to 3 factorial a3 plus 4 times 3 times 2 A4 times 0, which means P triple prime 4 is equal to 3 factorial A3, which means 4 over 3 factorial is equal to A3. And last but not least, I've got the fourth derivative of x will be the derivative, well, okay, that's gone. This just becomes 4 times 3 times 2 times 1, A4. There's no zeros to plug in here. I actually can find out that P4 of 0 is just equal to 4 factorial A4. And therefore, 5 is equal to 4 factorial A4, which means 5 over 4 factorial is equal to A4. And plug it in, you get your answers. I will just point out that I have all of my A1, A0, A1, A2, A3, and A4. I plugged those into the original function that was given to me in the activity, and I get this. Alright, that's a pretty fun activity. Now, homework, posted on my website. Feel free, go back and look at it. Taylor Series. This is actually a section entitled Taylor Series and Maclaurin Series, but a Maclaurin Series is a special type of a Taylor Series. You'll learn that as we go along. But let's assume that there is some polynomial that matches any function. That polynomial will take on the form P of x is equal to a0 plus a1x plus a2x squared plus a3x to the third plus dot 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 a sub n x to the nth. I will point out that this is very similar to what we just used in the do now. The only difference is now we're going up to the nth term, so we're going infinitely. Let's do some exploring to find the polynomial to represent the function f of x is equal to sine of x. So basically we want p of x to equal f of x. We have sine of x is equal to a0 plus a1x plus a2x squared plus a3x to the third plus etc., 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 a sub n x to the n. What number could we plug in to find the first number? I'm just going to point out we could plug in 0 just like we did on the do now. So I just want to point out here, we want, you're going to need a little bit of space for doing these calculations. I'm hoping that this is enough space, but if it's not, I got the back too. Alright, cool. So we've got f of x is equal to sine of x. And I'm going to recommend that you guys set up your paper exactly like this. Do 2 columns. Left-hand column you're going to have as your f of x. Right-hand column you're going to have as your p of x. And again, we want f of x to equal p of x. So our f of x is equal to sine of x. Our p of x, I'm just going to copy it directly off of this, this page right here, the previous page. And it's going to be a0 plus a1x plus a2x squared plus a3x cubed plus a4x to the fourth plus a5x to the fifth plus a6x to the sixth plus a7x to the seventh. Ideally, we would go on forever, but we don't have that much room on our paper to go forever. So I'm just going to go up to the 7th, and hopefully a pattern emerges. Hint, there's going to be a pattern that emerges. So what I look at here, I've got f of 0 is going to be equal to sine of 0. And sine of 0, just, doing my real quick unit circle. Show you my rough work right here. Zeros right here. I know that's at 1, 1, 0. So sine of 0 is equal to 0. P of 0, I could, I'm going to do this once just to illustrate to you guys, but again, this falls back on the do now. a0 plus a1 times 0 plus a2 times 0 squared plus a3 times 0 cubed. You guys, I hope get the picture that anything involving with an x attached to it, since they're becoming zeros, they are negligible, and we end up with p of 0 is equal to a naught. What we can now say is f of 0 has to equal p of 0, so therefore, well, let's just write that out. F of 0 equals p of 0, because again, we want the function to equal the function to equal the polynomial value. We have f of 0 equals p of 0. That means 0 equals a naught. All right? Now we're going to do the exact same thing that we did on the do now for a whole bunch of times. We're going to find f prime of x. F prime of x is going to be, I believe, cosine of x. Over here, we can find p prime of x, and I know a naught gets knocked off. I'm going to shift this over, unlike I did on the do now where I had it stepped in. I just need the room on my paper for this. So this is going to be a1 plus 2a2x, taking the derivative of a2x squared, plus 3a3x squared, taking the derivative of x cubed, plus 4a4x cubed, plus 5a5x to the fourth, plus 6a6x to the sixth, plus 7, no, to the fifth, 7a7x to the sixth, dot, dot, dot. There's a dot, dot, dot there at the end. I now find f prime of 0. That's going to be cosine of 0. Again, just go into my rough work up here. That's 1. It's equal to 1. P prime of 0 is just going to be equal to a1. Now I know f prime of 0 has to be equal to p prime of 0. So therefore, 1 equals a1. Keep the party going. I find f double prime of x. Derivative of cosine is going to be negative sine of x. Over here, I find p double prime of x. That's going to be, okay, so 2 times 1, a2, plus 3 times 2, a3x, plus 4 times 3, a4x squared, plus 5 times 4, a5x cubed, plus 6 times 5, a6x to the fourth, plus 7 times 6, a7x to the fifth. Whew, a lot in there. Fortunately, I don't need all those at the end there. All I need is f double prime of 0, which is negative sine of 0, which is 0. P double prime of 0 is going to end up being that 2 factorial a2. Set them equal to each other, and all of a sudden I have 0 equals 2 factorial a2. Hey, that's nice. Look at that. That factorial matches the subscript there. And I actually have just the second derivative. Oops, let's make that into an arrow. Second derivative divided by 2 factorial is equal to that a2. So a2 is equal to 0, really. Third derivative, okay, this is going to get messy at some point, is going to be negative cosine of x. Derivative of negative sine is negative cosine. P triple prime of x is equal to gonzo. Here we've got 3 times 2 times 1, so 3 times 2 times 1, aka 3 factorial, and corresponds with the subscript. That's nice. That's nice. Look at this. 4 times 3 times 2, a4x. Note that the subscript still matches that first number there. That's pretty cool. Plus 5 times 4 times 3, a5x squared, plus 6 times 5 times 4, a6x cubed, plus 7 times 6 times 5, a7x to the, looks like fourth over there. a lot going on there. I've got f triple prime of 0 is equal to negative cosine of 0, which will be equal to p triple prime at 0, which is just 3 factorial a3. Everything else is non-essential. We end up with, let's call that negative 1. We end up with negative 1 equals 3 factorial a3, which means I've got negative 1 over 3 factorial is equal to a3. Now let's just go back here, and I will remind you that we're trying to fill out this polynomial. So I'm just going to go through. I've got a naught. A naught is 0. Could you guys see that? A naught right here is equal to 0. So I've got 0 plus a1x, a1. You guys can actually see it without flipping your papers here. a1 is equal to 1. So this becomes 1x plus a2 is 0. So 0x squared. A3 was negative 1 over 3 factorial. So this becomes minus 1 over 3 factorial x cubed. So really, my polynomial here, I'm just going to skip a little bit, 1x minus x cubed over 3 factorial. I can't see a pattern because I only have 2 terms here. So I'm going to go back and see if I can establish a little bit more of a pattern. So I'm going to go and get the 4th derivative. So f4 of x is going to be equal to derivative of negative cosine is sine x. P4 of x is going to be equal to gonzo 4 times 3 times 2 times 1. A4, again, note the first number in that factorial is corresponding with the subscript here, plus, we've got the A5 now, 5 times 4 times 3 times 2, 5 times 4 times 3 times 2, x, plus 6 times 5 times 4 times 3, x squared, that's this guy right here. Oh, am I going to have enough room for it this time? 7 times 6 times 5 times 4, a7x cubed. Hadn't seen that guy in a while. All right, cool. So now I've got f4 of 0 is equal to sine of 0, which is equal to 0. 4th derivative of the polynomial at 0 is just equal to 4 factorial a4. 0 equals 4 factorial a4, therefore 0 over 4 factorial equals a4. I'm just going to take a pause here and notice how the subscript that we're on, if it's even, we're getting 0 as our coefficients. It looks like in my polynomial I'm not going to have any even exponents here. So let's go 5th derivative. 5th derivative of sine. Oh, hey, wait a second. Are we repeating the cycle now? Because the 4th derivative was the same as the first function. So the 5th derivative is just going to be cosine of x. I think over here we got to do a little bit more contemplation here, unless we can see the pattern. I mean, there is a pattern here. Gonzo, 5 times 4 times 3 times 2 times 1. Oh, there was, oh crap, I lost something. Oh, there was an A5 in there. A5 plus 6 times 5 times 4 times 3 times 2. There's an A6 in there. Maybe that's why I had so much room. A6x plus 7 times 6 times 5 times 4 times 3a7x squared. Finding the 5th derivative at 0 is cosine of 0, which is equal to 1. 5th derivative at 0 is just going to be equal to 5 factorial a5. I can now see that I have 1 equals 5 factorial a5, 1 over 5 factorial equals a5. I go back over here. I'm really hoping that I can see a pattern at this point. I'm really hoping that third one, so now I'm looking at the fourth one. So the fourth a4 is 0. So this would become plus 0 x to the fourth. Next, the fifth one. Fifth one was a5 is 1 over 5 factorial. So this become plus 1 over 5 factorial x to the fifth. Looking down here, I don't need to put down the fourth one. I can just put down the fifth one. So this become plus x to the fifth over 5 factorial. I can see the pattern now. Notice how only non-zero terms that I have here are the odds, and I have an alternating of a sign. So I'm looking here, just extending the pattern. I think the next non-zero term is going to be x to the 7th over 7 factorial. And the next term is going to be a plus, and this time it's going to be x to the 9th over 9 factorial minus x to the 11th over 11 factorial. So really all we're looking here is the alternatingness of the sign, and we have the odd exponents here. So if I want to put out the general term, we saw from the last lesson, to show the alternatingness, we're going to have that -1 to the nth, so that the evenness makes it positive, the oddness makes it negative, and we have to have x to the odd number. Easy way to do this is to recognize what an even number is. An even number is divisible by 2, so 2n is an even number. An odd number is 1 more than that. This would be 2n plus 1 over that 2n plus 1 factorial. And 2n plus 1 just means you're counting by odds, and then plus dot dot dot. If we want to put this in sigma notation, it would be the summation from n equals something to infinity. Remember from last lesson, I didn't put in the initial index until I put in the, tested it out a little bit. So -1 to the nth, x to the 2n plus 1 over 2n plus 1 factorial. And then looking back at that first term, if I plug in 0, this is going to be positive, and that'll be x. Okay, cool. So 0. Cool. Now, that was a lot. That was a lot of stuff. By the way, this is true. Sine of x is equal to this right here. That is absolutely 100% true. That's something that you'll probably want to memorize for the AP test. And I'll give you some tips and tricks on how to memorize it. There's, the pattern there. You can actually memorize it fairly easily. What I want you guys to do, well, actually, before we get there, what we just made is called a Taylor polynomial. Actually, the Taylor polynomial is just that's a first order Taylor polynomial. That's a third order Taylor polynomial, fifth order Taylor polynomial, seventh order Taylor polynomial, ninth order. Generally, on the AP test, I've seen it occur where they say give the first 3 non-zero terms of the Taylor polynomial. The Taylor series is all of the terms together. That's the Taylor series. We have just generated a polynomial that represents what sine of x is. And if you remember when I taught you sine and cosine, I told you they're transcendental functions. We have just transcended mathematics. We've gone above what algebra can comprehend, which is pretty freaking cool. I want you to use the same process to try to do the Taylor polynomial for cosine of x. I'll pause here for a second while you pause the screen and try it out. Just do the exact same thing. And here's all my work here. You can see again, trying to keep it organized, where I've got f of x on the left-hand side, p of x on the right-hand side. I even wrote out the polynomial up there. To get the fourth order Taylor polynomial, I just went to x to the fifth. And you can see when you get down to the bottom here, it actually ends up being nearly identical to that sine of x function. The one difference here, instead of being odds, we have evens. So evens down here, we've got negative 1 to the n, x to the 2n over 2n factorial. What we now can say here, another thing for you to memorize, cosine of x is equal to the summation from n equals something to infinity of negative 1 to the n, x to the 2n over 2n factorial. Again, I'm just stealing from my nth term here. And if I wanted to make sure that this works out, I can do a 0 power. That would be positive. That would be 1. And 0 factorial is 1. So n equals 0 to infinity. Before I tell you exactly what a Maclaurin series or a Taylor series is, I do want to point out again that, where is it? Sine of x and cosine of x are very similar to each other, just noting that sine is all of the odd exponents, cosine is all of the even exponents. That's an important distinction to make. One thing that I learned a couple years ago is how to memorize this. If I know this graph of sine looks like this, and I know the graph of cosine looks like this, and I can remember what even and odd means for polynomials, this becomes really easy. Because this is an odd function. It's symmetric about the origin. All odd exponents. Down here, this is an even function. Symmetric about the y-axis. All even exponents. When I learned that, that was just mind-blowing. That is really freaking cool to keep in mind. So there's a nice way to memorize that. Again, you're going to have to memorize. Now I'm going to tell you, those are called Maclaurin series. A Maclaurin series is a Taylor series generated with the center at 0. Now I will point out, when we did all of these calculations, and we did a lot of calculations, anytime we got to this part where we had the nth derivative is equal to a sub n, our coefficient of that a sub n was n factorial. So each term in the Maclaurin series is going to be equal to the derivative at 0, and you're going to divide by the order of the derivative factorial. So this is a formula you just straight up need to memorize. I cannot emphasize that enough. You need to memorize this formula. A Maclaurin series is equal to f of 0 plus f prime of 0 x plus f double prime of 0 over 2 factorial x squared plus f triple prime of 0 over 3 factorial x cubed plus etc., etc., etc. The nth derivative at 0 over n factorial x to the nth. Or if you have a Taylor series, more generally, a Taylor series is generated with a center not at 0. It's all the same stuff, except instead of doing f of 0 or f prime of 0, you do f of a, and the coefficients become x minus a. Now I do want to point out, looking back, I can curtail some of the work if I know this formula. So I now know that since I'm generating the Taylor polynomial at 0, all I really have to do is find f of 0. Since f of x is equal to cosine of x, f of 0 equals 1. I gotta find f prime of 0, so f prime of x is equal to sine of x. F prime of 0 is equal to 0. F double prime of x is equal to negative cosine of x. So f double prime of 0 is equal to negative 1. F triple prime of x is equal to negative sine of x. So f triple prime of 0 is equal to 0. This is the amount of work that I would do, and then I would really capitalize on this formula, and I would just say, oh wait, we wanted to go to the fifth order, so maybe I should get up to the fifth derivative. 4 of x is equal to negative cosine of x. So the fourth derivative at 0 is equal to negative 1. And fifth derivative, you guys already know that's not really necessary. Fifth derivative is going to be sine of x. Fifth derivative is going to be 0 at 0. So if I was doing this, I would now just go in and say the fifth order polynomial, I can call that p sub 5 of x is equal to f naught 1 plus, or f of 0, f prime of 0, 0 x plus f double prime of 0, negative 1 over 2 factorial x squared plus f triple prime 0 over 3 factorial x cubed plus, wait a second, oh, this was supposed to be negative, this was supposed to be positive, that would make this positive, that would make this positive, and this negative. Okay, I knew I screwed something up here. Plus f, the fourth derivative at 0. Okay, now I'm catching my feet. 1 over 4 factorial x to the fourth plus 0 over 5 factorial x to the fifth. That's the amount of work that you really should do. You'd have 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. So that's, I'm just trying to show you, you can summarize your work quite a bit if you know these formulas. Alright, cool. Fourth order Taylor polynomial that approximates y equals cosine of 2x near x equals 0. So I'm just going to run through the quick work to do this. So here, I know that in order to use this formula, and again, since I'm centered near 0, that's going to be a Maclaurin series. All I have to do to find the fourth order, I need to find f of 0, f prime of 0, f double prime, all the way up to the fourth derivative at 0. So again, here, I know f of x is equal to cosine of 2x. So f of 0 is equal to cosine of 2 times 0, so cosine of 0, which we just did, is 1. F prime of x is equal to negative 2 sine of 2x. F prime of 0 is equal to negative 2 times 0, 0. F double prime of x is equal to, okay, chain of 2, negative 4 cosine of 2x, which means f double prime of 0 is equal to negative 4. F triple prime of x is equal to, well, derivative of cosine becomes positive, so positive 8 sine of 2x which would be equal to f double prime of 0 is equal to 8 times 0, 0, crap. Okay, fine, whatever. F fourth derivative, oh good, we're almost there. Derivative of 8 would be, oh well, the derivative of 8 sine of 2x, I have a chain of 2, so 16 cosine of 2x, which would be equal to fourth derivative at 0 is equal to 16. So now again, I capitalize on this formula right here, the Maclaurin series. I have my fourth order Taylor polynomial, p sub 4 of x is equal to f of 0 plus f prime of 0, 0 over 2 factorial, over 1 factorial, x, plus f double prime of 0, negative 4, over 2 factorial, x squared, plus third derivative at 0, 0 over 3 factorial, x cubed, plus fourth derivative, 16 over 4 factorial, x to the fourth. And we don't need the ellipsis because it just asks for the fourth order Taylor polynomial, not the nth term. So look in here, we know that this becomes 1 minus 4 over 2 factorial x squared plus 16 over 4 factorial x to the fourth. Perfectly alright to leave it this way. However, I happen to know that 2 factorial is just 2, so this could be 1 minus 2x squared plus 4 factorial, 3 times 2, 24, 16 24ths ends up being 2/3 x to the 4th. So either one of those is acceptable. Now, I know some of you are looking at the next page and realizing that I didn't actually do it this way. There is an easier way. If you had remembered what cosine of x is equal to, so cosine of, let's just call it box, is equal to, and I'm just cheating off of what I have down here. The fourth order would be 1 minus box squared over 2 factorial plus box to the 4th over 4 factorial. And heck, let's even toss in the nth term. It's negative 1 to the nth box to the 2n over 2n factorial. Now the only difference between cosine of x and cosine of 2x, I went in, and let's see if I can get a fancy colored pen here. I went in and changed the input into 2x. So all these inputs are now 2x. And it looks like I've got, put those in parentheses here, I now have got 2 squared, 4, x squared, 2 to the 4th, 16, x to the 4th. I get the same thing as up here with very minimal work. I can actually find out that cosine of 2x is equal to 1 minus 2x squared over 2 factorial plus 2x to the 4th over 4 factorial. And I'm all right with you leaving it that way. That's perfectly fine. And we can even now put in, like I said before, dot, 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 the nth term. Negative 1 to the nth times 2x to the 2n over 2n factorial. And a lot of times AP is going to ask you to do that, where you just plug stuff in to a known Maclaurin series and get a new Maclaurin series out of it. And you can see over here, again, the same exact work that we had just then. I think we're almost done. We're very nearly there. Taylor series generated by f of x equals e to the x at x equals 1. I'm going to point out we're not centering at 0 this time, are we? We're centering at 1. So in order to do this, I need to go more accurately into the Taylor series rather than the Maclaurin series. And again, the only difference here is we're going to be taking it at a instead of at 0. And each polynomial term is going to be x minus a to the 0, or to the nth power. Here, it's important to note that a equals 1. When it says generated at x equals 1, that's giving you the center. So I'm just going to go through here. I've got f of x is equal to e to the x. That means f of 1 is equal to e to the first, e. F prime of x is equal to e to the x. That means f prime of 1 is equal to e again. F double prime of x is equal to e to the x, which means f double prime of 1 is equal to e. You do this until you see a pattern. I see a pattern that every derivative at 1 is just going to be e. So therefore, my Taylor polynomial is going to be, let's see, just using my formula, and you can hear the shuffling of the paper because I'm going back to this. I've got f of a. So f of a is e plus f prime of a, e times the quantity of x minus a, plus f double prime of a, e over 2 factorial x minus 1 squared, plus, and I didn't actually do it, but I happen to know that the third derivative at 1 is going to be e over 3 factorial times quantity of x minus 1 cubed. I know that whatever derivative I get to, I'm going to have derivative of e at 1 over n factorial times quantity of x minus 1 to the nth, and I'm done. I really like putting it in sigma notation, so I'm going to go from n equals something to infinity. I just slap my nth term over here, e over n factorial times times the quantity of x minus 1 to the nth. And if I just plug in 0, okay, 0 factorial is 1. E over 1 gives me 1. And then, yeah, okay, cool. Yeah. To the 0th power gives me 1 there as well. All right, cool. There we go. And you can see over here, it looks like I went to the exact same step there, just the second derivative. These right here, you should probably have these memorized for the AP test if you are taking the AP test. I will point out that these two are just geometric series, which we did last lesson. This one, super important. I like to think that that's the easiest one to work with. E to the x is 1 plus x squared over 2 factorial plus blah, blah, blah. All it works down to is the exponent matches the factorial for the denominator. Sine of x, that's an important one to know. Cosine of x, I already told you to memorize those two, and I even gave you the hints on how to remember which one is which. These I've never seen on the AP test, so that's not to say that they won't show up, but especially with them being lax in what they have there, you might not have to memorize those ones. Yeah, I might post a separate video involving these three Maclaurin series, just because it's a really cool thing. It's one of my favorite things in math. So yeah, Euler's identity. Look for that video. Hey, cool. Look at this. I've got these Maclaurin series, and there's like 4 problems on your homework that make you do something like this, where you have to just look at an established series that you have here, like x squared cosine of x. We already know what cosine of x is, right? So x squared times cosine of x is going to be equal to x squared times the series for cosine of x, which would be cosine is even, so 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And you just keep doing this until you get a feel for it. Initially, when you do it, you're going to have to just do a bunch of terms to figure it out. I was tutoring someone a couple years ago that he was able to do this if he wrote out the terms, but he always refused to write out the terms because he was trying to be one of those lazy teenagers that you have out there. Negative 1 to the nth times x to the 2n plus 1 over, no, not 2n plus 1, just 2n. It's cosine, so even. And here, I can just distribute. I've got x squared times 1 gives me x squared. X squared times x squared, x to the 4th over 2 factorial. Factorial doesn't change here. Plus, add x to the 6th over 6 factorial minus x to the 8th over 6 factorial. I can even do that at the nth term. Negative 1 to the nth, let's see, I can multiply x squared by x to the 2n. That just becomes x to the 2n plus 2 over 2n factorial. Or, in summation notation, summation from n equals blank to infinity of negative 1 to the nth, x to the 2n plus 2 over 2n factorial. And all of a sudden, I just look back and I can see if I plug in 0. It's going to work there. On number 2, I see that is actually pretty similar to this series right here, that first series, except I have to change the input to x cubed and multiply by x. You can actually see right here where I did that. Multiply by x, 1 plus x cubed squared plus x cubed, etc., etc., etc. E to the negative 2x is the same thing as e to the x, except you change the x to negative 2x. And I believe that is it. Keep an eye out for that video for Euler's identity, and don't forget to smash that like button.